Joining us for this fourth video in chapter 7, where we're going to cover the last of the 4 reactions that could happen with any substrate that has a leaving group. The first of those was introduced in chapter 6. That was the SN2 reaction. The last couple of videos we talked about SN1E1 reactions. Those were in competition with each other always. And then we're going to cover E2 reaction, which is very much driven by the base. The base is really the driving force. Unlike, remember E1 reaction, right? The rate determining step was all about just leaving group leaving. So maybe we didn't say. We should have said that's the rate determining step right there. In the E2 reaction, in the rate determining step, it's going to be the base that's going to matter. And in E2, as you could probably guess at this point, is elimination by molecular. So it's very much a base-driven reactions. We need to pay attention to that a lot. Okay, now for some reason this didn't show up on the Word document here. So here's sort of the generic E2 reaction, and where the base, of course, usually has definitely has to have a lone pair, often has a negative charge. And like we said, this is very much base-driven reaction, so this must be a good base. Okay. And the reaction goes like this. The base will grab the proton that's next on a carbon adjacent to the leaving group, because the proton carbon's electrons will fall down to form the pi bond, which will then kick off the leaving group. And notice there's sort of a nice flow of electrons that way towards the leaving group. And there's another caveat here, which is that the leaving group and the proton must be anti-coplanar. And that's kind of what it sounds like, that they need to be anti to each other in the Newman projection, 180 degrees opposite of each other, and they need to be coplanar, as in like in the same plane. And then what happens is, of course, you get the alkene product, and then the leaving group, of course, and base that's protonated. Now, it would be positively charged only if it started out as a neutral compound. But when you look at the kinetics, we would know that experimentally this has to be an E2 reaction, because the rate depends on both the substrate concentration as well as the base. So that's how we know in the rate determining step there's 2 things involved in here. This is second order. It's kind of like SN2 was a bimolecular reaction in the rate determining step, right? That this means, once again, 2 species are involved in the concerted rate determining step. And indeed, just like SN2, it's really a one-step mechanism. Like, so everything happens in one step. Okay. Now, and as you can imagine, right, like strong base, good base is often a good nucleophile. So this reaction tends to be in competition with SN2. Okay, so what are some factors that would favor E2 reaction? First, temperature, and this is something that should make sense to you after discussing E1 reaction. Remember the Gibbs free energy equation, and we talked about how at elevated temperature, right, the elimination reaction should be favored because there's more particles involved. Like starts with 2, but you end up with 3, right? So the chaos or disorder is increased, and for the same reason, right? Because for E2 reaction, delta S should be positive because you have more particles in the end, like E1 reaction. So E2 is favored over SN2, at high temperatures. Okay. Now let's look at the base factor, which often can act as a nucleophile as well. Right. Just the key point here is E2 is initiated by the base. That's why the base has to be stronger, good. Unlike E1 reaction was driven by just the substrate's leaving group leaving. So it's very different driving force, right? So for that reason, small base, strong bases can act as a good nucleophiles, then often SN2 favored under that condition if you have a small strong base. But strong and or exceptionally strong base or a bulky bases favor E2. Now, does small strong base favor E2? The small strong base can definitely do E2, but there's some competition possibility for SN2 as well. But if it's strong and bulky, then that's pretty much only favor E2 reaction. Okay. I think we skipped a factor here, so which is the substrate factor, and this can be primary, secondary, or tertiary. So it's not very picky about that. And this would be number 4. Let's think about the stereochemistry and regiochemistry. Okay. For E2 to happen, hydrogen and the leaving group must be able to be anti-coplanar. And we'll look at an example of that, but within the E2 reaction, Zaitsev product is preferred if you're going to use a relatively small base. Okay, and then again we'll look at examples of that, but the Hoffman product, which is the word that means maybe it means the opposite of Zaitsev. if a bulky base is employed. Okay, so let's think about some examples here. Here's an interesting substrate. There's potentially two different leaving groups. And let's say we're going to use methoxide, which is, of course, a strong but small base, right? This is this is T-butoxide, and this is a strong and bulky base, right? This is often abbreviated like that, T-butoxide. Anyway, so what's going to happen? Well, let's think about this. And because E2 has this anti-coplanar requirement, often it's important that you're going to think about the reaction in terms of 3D structure, not just sort of flat structure. Okay. That's not very good chair. So for that reason, I'm gonna draw the chair here, and here's the methyl group. Here's the bromine. Hope that makes sense that this is the most stable conformation of the chair, and I'm gonna draw some potentially relevant hydrogens on the adjacent carbons. Now, remember the anti-coplanar requirement. Oh, by the way, let me take a step back. I would encourage you to take a minute of a break from the video and then make this with your model kit. Otherwise, you may not be able to sort of understand what we're talking about here very well. But I want you to notice how these two atoms, the chlorine and the hydrogen, are anti-coplanar. They're both axial, so hopefully it makes sense that they're 180 degrees opposite of each other, and if you build a model, you'll see that these 1, 2, 3, 4 atoms are in the same plane, meaning sharing a plane or coplanar. And the methoxide would be able to grab this proton here, and then the chlorine leaves. Then the product is going to be it should look like that, and that's what we would expect with methoxide. Now, as opposed to let's see if I can just okay, what happens with T-butoxide? Well, because it's bulkier, right? Remember, this is CH3, so it's a bit of a bulk here. It would be difficult for a bulky base to grab this proton because this is kind of crowded with the methyl group. Now, we couldn't use this bromine as a leaving group because even though it's better leaving group, than chlorine, because there's no proton that's anti-coplanar to it. I guess we forgot to talk about that earlier. There's no anti-coplanar proton to this. You might think this is it, but you'll notice they're not anti to each other. They're like a gauche, and they're not in the same plane, right? So what's going to happen is the T-butoxide would go for this proton because on this carbon at least there's no methyl group, it's less crowded. Okay. And that would lead us to this product. Now, let's see if we can identify one of these as Zaitsev and then the other as a Hoffman product. I hope it makes sense to you that this is the Zaitsev product. It's the most substituted product, and then the bottom one here would be the Hoffman product from the same starting material. Okay, that's how we would distinguish those two. This is tetrasubstituted alkene, this is trisubstituted. Okay, and then we are saying that what happened here is because of the less sterically hindered proton was grabbed to make the Hoffman product. Now, so that's one example. What about like a linear molecule example like this? If we treat this with triethylamine, which is not like a strong base, but it's a pretty good base. It's good enough base for E2. And notice it's kind of a suited, base that's really suited for E2 because it's pretty good base, but also it's bulky. It's got like 3 ethyl groups coming out of the nitrogen. Now, how would this work? Well, let's think about this. The key idea is that, again, the proton on the leaving group has to be anti-coplanar. For a linear molecule like this, I think the easiest thing to do is to think about the Newman projection of if I look down on that bond, the way it's drawn, hope it makes sense to you that the Newman projection would look like methyl group on the right, hydrogen on the left, phenyl pointing down. On the front carbon in the back, you would see the phenyl pointing up. To my right is bromine, and then to my left is hydrogen. And here's the leaving group, the bromine, right? And indeed, there's a proton that's anti to it, and it would be coplanar. And once again, I would encourage you to build a model of this so you can see it. Now, here's triethylamine. So this will be able to grab that proton, and then that leaving group leaves, which would give you, if you think about the product in terms of the Newman projection here, the product should look kind of like this, right? I want you to notice that the 2 phenyl groups are in the trans geometry, opposite from each other across the double bond, and this is the same as oops. Right. Because when that proton was taken off here, this product could have actually looked like this, or it could have could have looked like that, depending on which way this bond was rotated. And again, this is something I think you might want to play with the molecule model kit to really understand. But because of this, we know that this is the major product. When I say because of this Newman projection requirement or E2 requirement for anti-coplanar, as opposed to, let's think about this example. This is a diastereomer of the earlier example. Now, what kind of transition state with this required. And once again, the product could be either the one where the two phenyl groups are trans to each other, or the two phenyl groups are cis to each other. And of course, thermodynamically speaking, right, this is not as stable because you got two big groups that are pretty close to each other. But if you draw the Newman projection of the molecule as drawn, once again, methyl on the right, hydrogen over here, phenyl, and phenyl coplanar, but the bromine is pointing this way this time. And so this time what we notice is that the proton here and the bromine here, this is not anti-coplanar. So you can't do E2 on this. So we need to, what needs to happen? Well, the bond here is a single bond that can rotate. So if rotation happens, right, I'm gonna keep the front groups the same, but if this rotates, let's say in this direction, the bromine and whatnot rotates in that direction, so the bromine's over here, then hydrogen's over here, and the phenyl group will be over here. Hope that makes sense. And again, build a model if this is very confusing, but at this point now the triethylamine can come in, grab that proton, the leaving group leaves and gives us the alkene or olefin product where here's the phenyl and a hydrogen. You notice that the two phenyl groups are cis to each other. Okay, so we should be getting this product as the major. Yeah, from that diastereomer. So hope that makes sense. The key idea is when the E2 reaction happens, here's the E2, the proton on the leaving group has to be anti-coplanar, and that's the conformation that gives you the product, and the product stereochemistry is sort of determined by that, right? So with this isomer, that's your major product. With this isomer, that's your major product from that E2 requirement. So we'll pick up from here in class.